Hey, C Block Physical Science class. I just wanted to go over last week's quiz so that you can use it to prepare for tomorrow's quiz. So here we go. I'm looking at last week's quiz. I'm on the proficiency side, so lowercase a, and the question says, a box is pulled at constant velocity along a rough surface by a rope. In the space at right, draw and label a free body diagram to show all of the forces acting on the box. Alright, so here's our box. You already have this written on your quiz, sliding along the floor. Alright, so first of all, what is keeping the box from floating around in the air? Gravity. So there's my dot for the free body diagram. Force of gravity is pulling the box down. Now, what's keeping it from plummeting towards the center of the earth? It's not falling right now, is it? That is going to be the normal force, Fn. Right? Notice that the force of gravity and the normal force arrows are about the same size. If I really wanted to, I'd get a ruler out and make sure they were exactly the same size, because they are. But I'm not going to do that. I'm going to put a little slash on each one so that any viewer knows that these arrows are intended to show equal length, thus equal magnitude of force. Alright, now the rope is pulling in this direction, so we definitely have that. And what's that force called? Force of tension, or the Tarzan force, as Mr. Yando likes to say. Now, because the box is moving at a constant velocity, that means all the forces are balanced. So that means that we must have a force of friction that is exactly the same as the tension. Otherwise, the box would be speeding up or slowing down. And that would represent a non-constant velocity. So this is the FF, or force of friction. Now these two arrows, the one pointing to the left and one pointing to the right, are the same as each other. They don't have to be the same as the ones that are pointing up and down. So I put two slashes on those to show that those two are intended to be equal. Alright, now that I've gotten that far, I'm going to reread the question and make sure I've answered everything that I'm supposed to do. A box is pulled at constant velocity along a rough surface by a rope. In the space at right, draw and label a free body diagram to show all the forces acting on the box. I've done that, so I'm ready to move on to the next problem. Alright, problem number 2. The same box's velocity is constant, 2 meters per second to the left. Explain whether the forces on the box are balanced or unbalanced and how you know this. Well, those forces, as we just said, are balanced. And we know this because it's moving at a constant velocity. Unbalanced forces would result in either a positive or a negative acceleration. Acceleration is a change in velocity. Alright, that's number 2. That's all we need. We need to say that they're balanced, and we know this because the box is moving at a constant velocity. The block shown is at rest on the surface. It looks like this. There's the surface. And we have this. We've got a normal force drawn for us. Surface is where that's coming from, and that's 50 newtons. Okay. We have force. So now we've got the force of a rope, force of tension, pulling this way, 120 newtons. So Ft from the rope equals 120 newtons. And what it says is that we're supposed to add any necessary forces with direction and magnitude. So which direction and how much, how many newtons, to the drawing below. Now, we know that we are going to need a force that's exactly the same as the force of tension. and that's going to be the force of friction. It's also going to be 120 newtons, and we know that these two forces are balanced because the block is moving at a constant velocity. What is that velocity? 0 meters per second. The block shown is at rest, and 0 is a perfectly legit constant velocity to be going at. So there it is. We have our 120 Newton force of friction pointing in the opposite direction of our force of tension. And that's all we need for that. We have the direction and we have the magnitude. Next problem. So our next one, these are the mastery problems, so we're on page 2 now. So uppercase A, a falling box has reached a constant velocity, which is called terminal velocity, and is no longer speeding up or slowing down. Draw and label both a system schema and a free body diagram to show all of the forces acting on the box. So, we'll start with the system schema. Mr. Yondo has started this off for you. Here's our falling box. Remember, it's falling at a constant velocity. So, what's causing the box to fall? Well, the Earth is. So we'll put Earth down here. Earth. And what else is at play here? What's causing the box to reach terminal velocity, or what's causing it to no longer speed up? And that's going to be air pushing against it. So we'll draw air out here. And both of these things are influencing the box, and we can draw a circle through that. And there is our system schema. There really isn't anything else left that we have to do with that. So that's our system schema. Now let's take a look at the free body diagram. There's our dot representing the box. We've got gravity pulling the box down to Earth. That's Fg. And then we have the force of friction pushing back up on the arrow, pushing back up on the box as it falls down. And the frictions of the air that's sort of rushing around the box and kind of causing it to no longer speed up as it plummets towards the Earth. We know that these two forces are equal, otherwise the box would be speeding up or slowing down. And those are all of our forces acting on the box. This is our free body diagram. All right. B, the box's velocity is constant, 120 meters per second. This is B, so we're adding on to this. And we explain whether the forces on the box are balanced or unbalanced and how you know this. Again, we know that the forces are balanced because it is no longer speeding up or slowing down, which is another way of saying that its velocity is constant. So that's what's happening. We have balanced forces because the velocity is constant. It's no longer speeding up or slowing down. All right, that takes care of uppercase level B. And lastly, we've got C. So we have a graph here. And let's see, here's our box. And we have a force of friction equals 4 newtons. And we have force of gravity equals 3 newtons. Now let's read the problem. Oh yeah, that's it. Okay, so the block is connected to a rope that is not shown in this diagram, and a tension is applied to the rope so that the block moves at a constant velocity. In other words, we're going to have to balance these two forces. Add one and only one force to the drawing, a force of tension, so that the block can move with constant velocity. Make sure that its direction and magnitude are clear. All right, so friction's pointing that way, gravity's pointing that way. We're going to be dragging the block something along the lines of this. So let's put a little scale in here. So there's 1, 2, 3 newtons. Actually, let me make 3 newtons right here at the end of the arrow. and 4 newtons, 3 newtons, 2 newtons, and 1 newton there. So what we know is that we need to have something that counteracts both of these at once. So we're going to need a line that goes up 3 and over 4. So this is an axis here, so 1, 2, 3, and 1, 2, 3, 4. So we need something that meets at 3, negative 4. So up 3 to counteract that, and negative 4 to counteract the positive 4 here. So that's going to put us here. So that's our direction. And now for the magnitude part of this, well, we know that this arrow looks a little bit longer than that arrow, and it's definitely longer than this one, but how big is it really? What we have to do here is we've got to use the Pythagorean theorem. And we know that this side is, let me move this over a little bit. I don't really need this anymore. This side is 3 newtons, but I'm just going to use the number 3 for now. This side is 4 newtons, and again, I'm just going to use the number 3. And this is the hypotenuse. This is the side of the triangle that is opposite of the right angle. So, Pythagorean theorem says that a squared, which would be this, plus b squared, which would be this, equals c squared, which would be this. This is c. C equals question mark. So a squared is 3 squared, and b squared is 4 squared, and then we still don't know what c squared is. 3 squared is 9, and 4 squared is 16, because 3 times 3 is 9, and 4 times 4 is 16, and that equals c squared as well. 9 plus 16 is 25. 25 equals c squared. You can use your calculator here. Take the square root of both sides. Square root of 25 equals the square root of c squared. And we get 5 equals c. So we find out that the c vector is 5 newtons big. And that's how you would do that problem. It goes the opposite way of both arrows, but at once. So up 3 to counteract the down 3, left 4 to counteract the right 4, all in one arrow. And then we can figure out the magnitude of it using the Pythagorean theorem. All right, I hope you have good luck on your quiz tomorrow. Happy Thursday.